Hello everyone. In this lecture, we will talk about the axiomatic approach to quantum mechanics. Quantum mechanics is one of those few theories in physics which have their foundations on a number of axioms. More specifically, there are 4 axioms that describes the theory of quantum mechanics. So we have quantum in the center, and this depends on 4 axioms. First axioms describe the states. So in this axiom, we discuss what can be called a state of a quantum system, what are its properties, what can be done with the state, what cannot be done with the state, and stuff like that. The second axiom depends on the observable. That is, what is the mathematical structure of observables? What is their relation with the states? What is their relation with the measurement operators? What is their relation with relationship with the dynamics of the system? And why certain mathematical structures can be called observables, and what kind of mathematical structures can be called observables? All those things have been attributed to the observable axiom. Third is the dynamics. This axiom talks about how a quantum system evolves. What is the dynamics of a quantum system, and what equation can describe it? So in this, we will talk about Schrödinger equation and how we arrive at the Schrödinger equation. And fourth axiom, last but not the least, is the measurement axiom. So in this, we will discuss what do we mean by a measurement on a quantum system, what are the outcomes of that measurement, what happened to the system after measurement, and how this measurement is related to the observables. So all these things, all these 4 axioms together contribute to quantum mechanics. If we understand these 4 axioms at its foundational level, then we don't need to then the quantum mechanics will not be as mysterious as everyone think it is. These 4 axioms is everything which is there to be offered by quantum mechanics. If we understand these axioms, there is nothing else to be understood. Everything can be derived from the understanding of these 4 axioms. So first one is about the states, that how we represent the state of the quantum system, and what are the things we have to keep in mind, what is their mathematical background of the states, state space, and stuff like that. The observable axiom tells us what mathematical structure can be called observables and why it is so, why that particular mathematical structure is called observable, and what are the properties of observables. The third one is about the dynamics, how we can evolve a quantum state in time, how the quantum system evolves in time, how do we perform transformation from one quantum state to other quantum state, and what are the physical processes and all. Those are later topics, but they all are subset of the dynamics postulate or axiom. And fourth one, which is the measurement postulate, and this tells us that what kind of measurements are allowed on the system, what happened to the system after measurement, what are the outcomes of the measurement, and how we can find the measurable quantity in the lab using this measurement postulate and the observable postulate. So we will start with the state. So for a quantum system is a physical system. So a mathematical structure which can contain every possible information about the quantum system should be called a state, can be a valid state. Let me repeat the statement. We have a quantum system, and let us say we have a hypothetical mathematical structure, and let us call it psi. And we don't know what this is at the moment. It can be a function, it can be an operator, it can be a vector, it can be a complex number, it can be anything. Right now, we do not know what it is. We only know that if we use it in a specific manner, in some convenient manner, then we can retrieve all the information there is to know about a quantum system. Okay, so what I mean by this is, if we are allowed certain measurements on the system, like position measurement, momentum measurement, temperature, and whatever measurement we can think of in the lab on a quantum system, if we perform those measurements, we will get certain outcomes in the measurement. Those quantities we should be able to retrieve from the mathematical structure psi. And if we can find such psi, then we will call it the state of the quantum system. So psi is the state of the quantum system if it contains all the information about a given quantum system. So, of course, we can always say that there is too much information in any given quantum system. So, how can any mathematical structure contain all the information? We'll talk about that soon when we talk about other postulates and a little bit more details of the states. But this is what we will base our whole course on, that our state is a mathematical structure which contains all the information about the quantum system. But there is a small catch here. When we say all the information, we only mean that the information that can be retrieved from an experiment, okay, or from all the possible experiments. So if quantum mechanics does not allow for certain information to be known, that information will not be contained in the state psi. But those are slightly more advanced topics. We will discuss them later on when we talk about other topics like the completely positive maps and state tomography and state preparation methods. When we talk about those things, we will know what we mean by what I just said, that there is certain information which is not knowable from the experiments, and that information will not be contained in the state psi. So, the mathematical structure of the state. So the state, whenever we write the state of a quantum system, we put this symbol. So whenever we see this symbol, we will mean that it's a quantum state, and it is called cat. So cat psi means the quantum state psi, and if we take the adjoint of this psi dagger, it will be this symbol, and that is bra psi. In the traditional quantum mechanics, the state psi is an element from the Hilbert space H, and this Hilbert space is the space which contains all the states of the quantum system. Let's say S. Quantum system is S. So we put subscript S here just to represent that this Hilbert space belongs to the quantum system S. So a state of the quantum system psi belongs to the Hilbert space HS, and all the states of the quantum system belong to this Hilbert space. So that is our first mathematical definition of the state, that it's a vector in the Hilbert space HS. Let me remind you that Hilbert space is a linear vector space over which we have defined the inner product and the metric of length, distance. Psi is also called pure state, as opposed to mixed state, which we will be discussing later on, not in this lecture. The property of this state psi is that psi is normalized, that the inner product of psi with itself is 1. Not just that, if we have two states, psi 1 and psi 2, they are the valid state and they belong to the Hilbert space HS, then their superposition psi 1 plus alpha psi 1 plus beta psi 2, which also belongs to the Hilbert space because that's the property of the Hilbert space, and that is also a valid state as long as alpha mod square plus beta mod square is equal to 1. So this normalization condition is very important, that the state should be normalized, and we can take the superposition of any arbitrary number of states, the sum over n, alpha n, psi n is also a valid state as long as sum over n alpha n mod square is 1, where alpha n's are the complex numbers. So these are the properties of the states here, that they should be normalized. The superposition, as long as it's normalized, is a valid state, and they are vectors in the Hilbert space HS. Although the state psi is a vector in the Hilbert space HS, not all the vectors in the Hilbert space are states. In fact, two vectors from the Hilbert space phi and psi are equivalent if, or they represent the same quantum state if psi is some scalar lambda times phi. So it means the set of all the states phi such that lambda times phi equals psi represent the same state. It means we can divide the vectors of Hilbert space into of uh, sets of vectors which represent the same state. Right? Like the way we defined here, that if two vectors are different only by a scalar factor, then they represent the same state. So in that way, a Hilbert space can be divided into set of such vectors. To understand what we are doing here, let us consider a two-dimensional Hilbert space. Two-dimensional real space, we have y-axis, we have x-axis. So this is R2, this is a two-dimensional vector space, and we can define the inner product as the Cartesian product. Then we have many vectors here. For example, we can take few vectors, 1 and 2 and 3. So these are different vectors. But now consider another vector. One is this vector, let us call it R1 vector. And we take another vector along this line, but up to a smaller distance, R2 vector. So there are two vectors, R1 and R2. They are only different in the size. So what we can do is we can find a vector R, which is R1 over R1 norm. So it's a unit vector, and it is R2 over R2 norm. And you can find many such vectors which will, if we normalize, it will become R vector. So we take that normalized vector. We take all the normalized vectors in this space, and each normalized vector will represent one quantum state. And in R2, a set of normalized vectors, if we take a set of normalized vector, that will make a circle. Because if we take the tips and if we join them, we get a circle. So this circle in the whole R2 space represents the quantum states. But this was a hypothetical example of R2 because it's easy to visualize. Now think of a Hilbert space, which is a complex vector space, which will be very hard to imagine, but just think of it as a two-dimensional, like R2 as a specific version of the Hilbert space. In that, we take all the vectors which are only different in the norm, and we identify it as one vector. So one normalized vector will be the representative vector of that. We find all such different vectors, and they all together will form a circle in R2, and they will form a more complicated mathematical structure in a more complicated Hilbert space, and that is called the complex projective Hilbert space. So we identify all the vectors which are different only in the norm as one vector, and we normalize it, and we take the collection of all the all the normalized vectors. This is the complex projective Hilbert space for HS. Okay, like we showed that the circle is the complex projective Hilbert space for the R. This is also called ray space. And ray space is the real space, or ray space is the space which contains all the quantum states of a given system, and all the points in a ray space are valid quantum states. Unlike the Hilbert space where all the vectors don't represent quantum states, but in ray space all the vectors represent quantum states. Next is observables. What are the observables for quantum mechanics is the question we will be addressing in this exam. So from the experience, although the states being a part of Hilbert space can contain complex numbers, but whenever we observe something, whenever we measure something, the outcome in a lab will be always real. So observable is some mathematical structure, let's call it Z, some mathematical structure such that the outcome are real. And the outcome should be distinguishable. They should be independent. In mathematical terms, it will be orthogonal. So we are looking for a mathematical object, mathematical structure, such that it has some quantity which are real numbers and some quantity which are some mathematical structure which are orthogonal. So one candidate for that are the Hermitian operators or self-adjoint operator. So if we have a self-adjoint operator Z, then we know it's Z equals Z dagger. That's the definition of self-adjoint or Hermitian operator. We know that if the operator is self-adjoint, then the eigenvalues are real and eigenvectors are orthonormal. So we can identify the eigenvalue as the outcomes in lab. So whenever we measure this observable, then the eigenvalues will be the outcomes of the measurements, and eigenvectors will be the states we will be getting. This. So in that way, the Hermitian operators satisfy the requirement posed by the physical consideration. So in quantum mechanics, we will consider Hermitian operators as the observable of the system. If we have a Hilbert space Hs and the dimension of this Hilbert space is D. So the Hilbert space we are considering is a D-dimensional system. So this can be a physical example of this can be an atom where we are considering only D energy levels of that atom. So one such quantum system will have dimension D, or spin half electron, then it has only two quantum states, so D becomes 2. So if we have a Hilbert space Hs where the dimension of the Hilbert space is D, then the observables or the Hermitian operator Z will be D by D matrices. And they belong to a set B acting on Hs. So this B is a set of operators acting on the Hilbert space H. So the operators which are allowed to act on the state or on the vectors of the Hilbert space H. We are representing that with B of H. So the Hermitian operator Z belongs to this set. Not just that, it belongs to this is a general set, so it belongs to the set of Hermitian operators. The Hermitian operators form a vector space. The set of Hermitian operators, set of all the Hermitian operators, form a vector space over real field. The dimension of this vector space is D square. So it means there are d square mutually orthogonal and independent Hermitian operators you can find in this vector space. For example, for d equals 2, we can have a basis for this vector space, and this is the polybasis. I'm giving one example. There are, of course, more than one example for it. So the polybasis have 4 elements. One is identity, is a 2 by 2 identity. Then we have sigma x, sigma y, and sigma z, where identity is 1, 0, 0, 1. Sigma x is 0, 1, 1, 0. Sigma y is 0 minus I, 0. Not 0 minus I, it's the element. And sigma z is 1, 0, 0 minus. So here, identity is the trivial operator, and the eigenvalues of that are 1 and 1. Sigma x has the eigenvalue 1 and minus 1. Sigma y has eigenvalue 1 and minus 1. Sigma z has eigenvalue 1 and minus. If we represent cat 0 as 1, 0 vector and cat 1 as 0, 1 vector, then we can see sigma z acting on 0 is just 0, and sigma z acting on 1 is just 1. So in that way, we can see sigma x acting on 0 will give us 1, sigma x acting on 1 will give us 0, sigma y acting on 0 will give us I times 1, and sigma y acting on 1 will give us minus I times 0. Not just that, the eigenvectors, so 0 and 1 are the eigenvectors of sigma z. Eigenvector of sigma x can be written as 0 plus minus 1 over root 2, and these correspond to eigenvalue plus minus 1. Similarly, eigenvectors of sigma y are 0 plus minus I 1 over root 2, and they correspond to plus minus 1 eigenvalue. Identity operator is the trivial operator. Every vector is an eigenvector of identity operator. So we don't need to mention that here. Since the polybasis is a basis for 2 by 2 Hermitian operator, any Hermitian matrix H can be written as sum over mu from 0 to 3, H mu, sigma mu, where H mu are real numbers. And mu sigma 0 is identity, sigma 1 is sigma x, sigma 2 is sigma y, and sigma 3 is sigma z. Although it's not required, but we can also define the inner product over the vector space of the Hermitian operator. So the inner product between two matrices A and B we can define as trace of A dagger B. So for Hermitian operator, it will be just trace of A times B. This is how we can define the inner product over the operators. Next is the dynamics of postulate, dynamics of quantum system. So in this postulate, we discuss how a quantum system evolves in time. Okay. So if we are given a quantum system in certain initial state, what is the state of the system after time t? And this is where the Schrödinger equation comes into the play. Schrödinger equation is what defines the dynamics of the quantum system. So how do we arrive at the Schrödinger equation? So first we notice that quantum mechanics is the wave theory. It is inspired from the wave equation. And the general solution of a wave equation is exponential of I k vector dot r vector minus omega t, where k vector is the wave vector, which tells us that the direction of propagation and the wavelength of the light. R vector is the position, omega is the frequency, and t is the time. So this is, so any solution of the wave equation will look like, it will be proportional to this. Now we see that in quantum mechanics, the first thing we know about quantum mechanics is the energy is quantized. So energy is always h bar times omega, where h bar is h over 2 pi, where h is the Planck's constant. So for a given frequency, if we have a wave of given frequency omega, then the energy of that wave is quantized. It cannot be any arbitrary value. It has to be an integer multiple of this h bar omega. So it means if we have a state psi of a quantum system, and we have some operator, some energy operator E, that should give us h bar omega times the state psi. This is the meaning of this condition, that if energy is h bar omega, so h bar omega is the eigenvalue of the state of the operator, energy operator, and if we have the state like the wave state, wave equation, solution of the wave equation, then the operator acting on this state should give us h bar omega times the state psi. So if we compare, if we say the psi is proportional to exponential of I k dot r minus omega t, from here we can see that if we have I d over dt of psi, we get h bar omega, or there is a h bar also, I h bar, the h bar omega times psi, the same state psi. So in that way, it seems that the energy can be represented, energy operator can be represented by I h bar d over dt. The time derivative is proportional to the energy operator. The second quantization, or not second quantization, the second thing in quantum mechanics is that the momentum is quantized. So the P is h bar k vector. If the state of the quantum particle is represented by this expression, where k bar is the wave vector, then the momentum, or the momentum operator or momentum vector of the particle is proportional to the k vector, or the momentum is inversely proportional to the wavelength. So if this equation has to be satisfied, then we can see that minus I h bar del operator acting on psi will give us h bar k vector dot k vector psi. We can substitute psi from this equation, and we can see that this is indeed true. So what we have established is that I h bar del d over dt is equivalent to the energy operator, and minus I h bar del operator is proportional to the momentum operator. Now we know energy is p square over 2m plus v of r, where p square over 2m is the kinetic energy and v of r is the potential energy. Now if we substitute it here, then we get I d or I h bar d over dt of psi will be equal to p square, which is h bar square over 2m del square psi plus v of r psi. So by arguing the energy quantization, momentum quantization, the solution of the wave equation, and the relation of the quantum mechanics with the wave equation, we have arrived at an equation in which on the left hand side we have time derivative, and on the right hand side we have potential energy and kinetic energy. And this is called the Schrödinger equation. And this equation characterizes the evolution of dynamics of a quantum system. Further, we can see that p square over 2m plus V of R, that is kinetic energy plus potential energy, is H, the Hamiltonian of the system. So we have a quantum system, and Hamiltonian is defined over that system. Hamiltonian for an isolated system is just total energy. So the operator H is the Hamiltonian operator, and the Schrödinger equation can be written as I H bar d over dt of psi equals H psi. And for an isolated system, H is time independent, so we can write formally the solution psi at time t equals exponential of minus I H t minus t0 over H bar psi of t0. Since H is Hamiltonian, it's an observable of the system, so it must be Hermitian. It means H has a spectral decomposition where we have lambda n and psi n as the eigenvalue and eigenvectors of the Hamiltonian, where n is from 1 to d, where d is the dimension. If for the case when d is 2, then we have Hamiltonian, which is lambda 1 psi 1 plus lambda 2 psi 2, or we can just say lambda 1, or we can say E1 for the energy. Let me put it here also, E1 ground state plus E2 the excited state. There are only two levels of the quantum system, so one is ground state and another is excited state. So we are assuming E1 is smaller than E2, so that we can call it ground state. Now in that case, if that is the case, then exponential of minus I H t minus t0 over H bar can be written as, since G and E are orthogonal to each other, this thing can be written as exponential of minus I E1 t minus t0 over H bar, or I would like to write E1 as H bar omega 1 and E2 as H bar omega 2, so that we can cancel H bar when we get t minus t0 omega 1 Gg plus exponential of I t minus t0 or minus I omega 2 excited state. What is the benefit of doing this? Now we have state psi 0, which also since it is a two-dimensional state and G and E are orthonormal basis, we can write psi 0 as some alpha 0 the ground state plus beta 0 the excited state, where alpha 0 and beta 0 are the complex coefficients, such that alpha mod square plus beta mod square is 1. Once we have this, we can easily write psi of t as alpha 0 exponential of minus I omega 1 t minus t0, that was t0 not 0, G plus beta 0 exponential of minus I omega 2 t minus t0, and this is how we can find the evolution of the quantum system. So what we did is we have a Schrödinger equation in which the time derivative of a state is equal to is proportional to the Hamiltonian acting on the same state. From here we can see the Hamiltonian is the generator of the time evolution in the quantum system. So if we are given a Hamiltonian, we can find the time evolution of any arbitrary state by decomposing the state into the eigenbasis of the Hamiltonian. And in that way we can proceed with the evolution. Now one thing to notice here is the evolution was done by an operator exponential of minus I H t over H bar. Here we have scalar t over h bar, we have another scalar minus I, and we have a Hermitian operator. So I times Hermitian or minus I times Hermitian is an anti-Hermitian operator. Exponential of an anti-Hermitian operator is a unitary operator. And this unitary operator is taking one state to other state. It so happened that this unitary operator is the time evolution operator, so the state evolved in time. But in general, t can be any arbitrary parameter, h can be any arbitrary Hermitian operator, and there is the I. So it means unitary transformations, unitary operators transform a state to another state, psi1 to psi2. So in general, any transformation from psi1 to psi1 to psi2 is governed by a unitary operator. If we see some transformation happening on a quantum system which is not unitary, then we can be sure that we do not have the full information about the system. There is another hidden part of the system which we cannot see. But if we include that part, then the whole dynamics will look unitary. The whole transformation will look unitary. So in that way, the dynamics and the transformations are governed by unitary transformation, unitary operators.